Today we're going to be covering ketones. Ketones are hydrocarbon with a carbonyl group, which is seen and we're double bonded together, and that's bonded to a non-terminal carbon. Example of this is acetone. These are the terminal carbons, and this is the carbonyl compound. That means that the carbonyl group is located somewhere in the middle of the hydrocarbon rather than carbonyl. The general formula of the ketone is R, C, double bonded to an O, R prime. Where the R prime group represents the remainder of the hydrocarbon, they can be the same or different. These are magnesium butadiene. There's a methyl, one C over here, whereas there are two C's on this side. However, in butanones, the R group on the left side of the carbonyl group is different than the R group on the right, but both sides are acceptable. Now that you know the basics of ketones, we'll move on to naming them. The first step in naming a hydrocarbon is to name the hydrocarbon parent chain, which in this case is 1, 2, 3, 4, 5, 6. That transfers to X, so it will be an hexane. The next step is to drop the E on the end of hexane and add O or hexano is what we'll have after. And step 3 is to locate the functional group. In this case, 1, 2, 3. Our functional group is working on the third carbon, and that will make it 3 hexane. From here, we'll have the lowest number. It's important to note the lowest number in the hydrocarbon. This could also be interpreted as 1, 2, 3, 4 hexanone, and that would be incorrect because of my build. So I'm going to move on and give the stage to Derek.
So let's talk about intermolecular forces. Ketones have London forces and dipole-dipole forces. Dipole-dipole forces are present because of the electronegativity difference between carbon and oxygen. Oxygen is partially negative with electronegativity of 3.44. Carbon is partially positive with an electronegativity difference of 2.55. The difference between these two atoms is 0.89, making the bond 4 go in, allowing for dipole-dipole forces to exist. Hydrogen bonding cannot exist in ketones because there's no hydrogen in oxygen. No hydrogen bonding to oxygen, nitrogen, or fluorine, eliminating the possibility of hydrogen. And as everyone knows, London forces are present because they exist in every molecule. The molecule as a whole is polar due to the dipole-dipole forces being present, as well as the overall shape of the molecule being asymmetrical. These things influence the properties of the molecules. Ketones are soluble in water because they are polar molecules. The solubility becomes more difficult, however, as the molecule becomes larger. For example, the solubility will be easier for propanone or acetone than it will be for hexane. Melting points and boiling points are also influenced by the size of the carbon chain. If we focus on hexanone, the melting and boiling points are higher than the hydrocarbon already because the addition of the double bond to oxygen. The melting and boiling points increase slightly because it takes more energy to break double bonds than it does to break single bonds. To give an insight, hexane is a normal molecule, has a melting point of negative 95 degrees Celsius, so just that has a negative 95 degrees Celsius. And hexanone has a melting point of negative 57, so quite a bit higher than hexane. And a boiling point of 126. By the addition of the double bonding of oxygen, the melting point increased by 38 degrees Celsius and the boiling point by 57. And again, As the carbon chain gets longer, more energy is needed, and the melting points and boiling points increase as the chain grows. Although ketones have higher melting and boiling points than the original hydrocarbon, the melting points and boiling points are lower in comparison to alcohols. Alcohols have a higher melting point and exists due to the hydroxyl group, the OH. This adds to the difficulty of breaking the bonds, increasing the melting and boiling points. So as to recap, ketones have London forces as well as dipole-dipole forces due to the carbon to oxygen electronegativity difference. The overall molecule is polar because it is asymmetrical, which allows ketones to be soluble in water. The melting points and boiling points of ketones are higher than the original hydrocarbon, but lower than their alcohols. And lastly, solubility becomes more difficult, and melting points and boiling points increase as the carbon chains become higher. Get it? Now we're going back to Todd.
The final lesson of ketones is reactions. Ketones can react in a combustion reaction or be created in an oxidation reaction. For the oxidation reaction, a second-degree alcohol can be oxidized by different strong oxidants like potassium permanganate, potassium dichromate, or sulfuric acid. These substances are put in place of the oxygen symbol in the equation. They're there to control the oxidation reaction. The hydrogen atoms are taken from the hydroxyl group and the single hydrogen bonded to the middle carbon. This creates a ketone with a carbonyl group and byproducts of water. This can be reversed by a process of hydrogenation. This process adds hydrogen atoms when needed, so a ketone plus a hydrogen turns into a second-degree alcohol with addition of heat or a catalyst. The final reaction we can do is combustion. This is noted here, and this is where oxygen is added to a ketone to make carbon dioxide and water. And that's all there is to know about ketones.